Okay, so last week we started looking at elliptic PDEs. These are the simplest type of PDE. They're steady state, so solutions do not depend upon time. So the solution to an elliptic PDE doesn't depend upon time. It doesn't depend upon the initial conditions. So you can have any initial conditions you want, you'll still get the same solution. Okay. What they do depend on, though, is boundary conditions. Okay, so last week we looked at the two-dimensional finite difference grid. So instead of just having a 1D grid like we saw a couple of weeks ago, with the elliptic PDE, and we're looking at the Laplace equation, okay, we have two spatial dimensions. We have the x and the y dimension. So what we do is we discretize our 2D space by inserting lots of finite difference nodes on a regular grid. Okay, so we have some nodes going across in the horizontal direction and some nodes in the vertical direction. So this is how we get our finite difference grid. Okay, couple of things to note. The spacing in the x direction is denoted by delta x, and the spacing in the y direction is denoted by delta y. Delta x and delta y don't have to be the same. Sometimes they are, to make calculations easier and make a lot of things easier, but they don't have to be the same. Okay, in lab sheet 3, if you've started that, in that particular case, delta x and delta y are different. Okay, but for the examples I've got in the notes, delta x is the same as delta y. Convention for labeling nodes. Okay, when we talk about nodes, we need to a method of addressing or indexing the nodes. Okay, the convention used is we go I in the x direction. Okay, so as we go up in the x direction, we use I as the index, and we use j in the y direction. So a node typically has two subscripts, I and j. I denotes how far along the horizontal direction we are. J denotes how far up the y direction we are. This is a bugbear of mine. This is something that always annoyed me. Matrix indexing uses row then column. Finite difference indexing uses column then row. Okay, so you've got to remember, you've got to flip them around. So instead of the first number denoting what row you're on, the first number denotes the column. So the I gives what column we're on, okay, and the J denotes what row we're on. So always bear that in mind. You don't have to have it that way around, but this tends to be the convention which is most often used in the literature. Okay, so that was finite difference grid we saw last week. Okay, and we looked at deriving a finite difference scheme to solve Laplace's equation. So Laplace's equation is simply the double partial derivative of u with respect to x plus a double partial derivative of u with respect to y equals 0. Okay, so this is Laplace's equation. We can use second order differences, which we derived a few weeks ago. Okay, so if we if we discretize the x direction and approximate it with a symmetric difference, and we do the same for the y, okay, we've gone from a differential equation to an algebraic equation. Okay, rearrange to make u ij the subject. Okay, a bit of algebra, and you get to this stage here. Okay, all I've done there is multiply throughout by delta x and delta y squared, factorized, and then sort of rearrange it to make uij the subject. This would give us a finite difference scheme if delta x and delta y squared were different. If delta x equals delta y, okay, this can all be simplified to this simple scheme at the bottom. Essentially what this is the four compass directions, north, south, east, and west. So the nodes which are next to our ij node in the north, south, east, and west direction, we add them all up and divide by 4. Okay, so that makes it, this is a very simplifying thing we can do here. Note this would not always be the case. Sometimes you may not have delta x and delta y being the same. But if they are, it simplifies to this. In fact, in the lab sheet 3, they're not the same. So you have to substitute in your delta x and delta y into that one to derive the finite difference scheme. Okay, that's a finite difference scheme. And we looked at this quite simple arrangement. So we have some 2D domain, and we've discretized our x direction using 5 nodes, and in the y direction we've used 4 nodes. Okay, the nodes on the boundaries are all boundary nodes. I've colored them in white here. Okay, these are boundary nodes, and we applied Dirichlet boundary conditions. Okay, that's when the value of the nodes are constant. Okay, we don't need to calculate these using our finite difference scheme. In fact, we can't, because there's no nodes outside. Okay, so these remain constant. The computational nodes, which I've colored in black, those are the nodes which we're solving for. So in this case, we've got quite a simple grid with just 6 computational nodes. Okay. And we looked at one method last week, the Jacobi method for solving those computational nodes. It's an example of an indirect method. Okay, indirect means we iterate over and over again until eventually 2 iterations are close enough together for us to say, okay, that's accurate enough. Okay, indirect methods are, in general, iterative methods. There are other forms, for example, Gaussian elimination and LU factorization, which those of you doing ODEs will see in the second term. That's a direct method. That will give you an exact solution. Indirect methods gives you an approximate solution, but it's damn close. Well, it's as close as you need it to be. Indirect methods are generally preferred for larger systems. Now here we've got a 6 by 6 system. You could do this using Gaussian elimination. Okay, but what if you had 100 by 100 or 1,000 by 1,000? It would just be too big. So we tend to prefer indirect methods for large systems. Okay, so estimates of the solution are improved until 2 successive iterations agree to some required accuracy. And with the Jacobi, what we do is everything on the right-hand side of the finite difference scheme, okay, is the kth value. Okay, so k is kind of like what iteration are we on? When k is 0, that's the initial values. When k is 1, that's the first iteration. K is 2 is the second, and so forth. So the next estimate of node ij is simply the sum of the current values of the north, south, east, west nodes divided by 4. Okay, and that allows us to, if we do that over and over again, it allows us to calculate the solution. And this is what we saw last week. It took 33 iterations to converge to a tolerance. So we want the norm of the difference between the 2 solutions to be less than 1 times 10 to the minus 6. And that took 33 iterations. Okay. Right, so that's what we looked at last week. So now I'm going to start going through from page 36 in the notes, and we're going to look at the Gauss-Seidel method. Now, the Jacobi method, nobody ever uses it. Okay, it's kind of used as a sort of an introduction into indirect methods, but it's just too slow. One of the reasons it's too slow is it wastes information. So as we go through our nodes, okay, if we go by row by column order, so we'll go through all the rows, all the columns on the first row, then we move up a row, go through all those nodes on that row, move up a row, etc. When we're halfway through that, we've already calculated the next estimate for half the nodes. So why don't we use them in our update of the node ij? Okay, so essentially, it's inefficient. It does not make use of nodes that have already been calculated. Gauss-Seidel method is very simply any nodes which have already been calculated for the current step are used as soon as they're calculated. Okay, so if we're using row by column order, the nodes to the west and to the south have already been looked at. Okay, what do I mean by that? I'm just going to go back to the grid. Okay, starting at this node, Okay, if we go for this row first, this is the first node. No other nodes have been calculated for the current iteration, so that's the same as Jacobi method. If we then calculate this node, okay, it's the north, east, south, and west sum. So we sum all those, but that node 1, 1 had just already been calculated. So why not use the new value? Okay, so that's what we're doing. The nodes below, so for example, this one uses these two nodes here. Okay. These would have already been calculated for the current step, for the current iteration. So why not use them? So the nodes to the west and to the south, we can say, okay, let's use the most updated value. And that's what we're doing here. So if you notice, the superscript, remember this isn't a power, it's just a superscript. The node to the south, which is that one, and the node to the west have the superscript k plus 1. That's because we're using the k plus 1 value. Okay, so that's the Jacobi method. Rubbish, generally rubbish, but it's used for sort of comparison and teaching purposes. That's what's called the Gauss-Seidel method. Okay, so we're going to step through the calculations now. So this is the same initial conditions and same boundary conditions as for the Jacobi method. Okay, if we sum, for some reason I've gone south, west, north, east on this one. Okay, the first one always going to be the same as Jacobi. Okay, for the first node in the computational nodes, we haven't updated any other ones yet for the current iteration. So it's always going to be the same as Jacobi. Okay, so we have 3.5. Next node along. Okay, so if we sum the south, west, north, and east, doesn't really matter what order. But from the previous node, we just calculated 3.5. So we've used that for the second node, okay, to give us a value of 2.8. Notice it's slightly different from the Jacobi method. In the Jacobi method, this 3.5 here would have still been 0. Okay, and move along another node. Okay, so we're using south, west, north, and east again. And again, the node to the west, the 2.8, has just been calculated. So we're using the most recent value of that node. Okay, step up a row. So we've done all the nodes on the first row. If we step up a row, okay, so we're using the south and west new values, and this 3.5 is used. If we were doing Jacobi, this would still be 0. And if we do the same for the other two, okay, that's what we get. Okay, the nodes are just bigger here, just so I can fit on the solution. Then the size of those nodes here doesn't mean anything. Okay, they're only bigger just so I can fit on those numbers. Okay, so that's the Gauss-Seidel method for calculating the solution to that Laplace's equation. Okay, so what I'm going to do now is I'm going to revisit last week. I had to go. We wrote some code, didn't we? If I find Moodle again. Okay, so what I've done to help you for your lab sheet 3 is I've actually put that code up here. Okay, so when you come to do lab sheet 3, you can use this code which we calculated last week in the lecture. So I'm just going to copy that. And what I'm going to do, that was using Jacobi method. Actually, I think that one there, but I use a nicer version. Okay, just going to run it just to make sure it works. I'm going to call it Laplace Jacobi. And there we go. It took 33 iterations to converge to that solution there. Okay, so we've done all the hard work. Okay, this program here, this is what we did last week. By the way, I've also put up a YouTube video on how to write this, because I understood you don't always want to go through all the lecture to just find this. So if you go to the Google Plus site, there is a YouTube video of me writing this. Okay, right, so we got the same equation. Okay, same starting value, same boundary conditions, all I'm going to do is I'm going to change this into the Gauss-Seidel method. And essentially, what we need is we need the nodes to the west and to the south to use the k+1 value. That's it. That's changing from Gauss-Seidel method, sorry, from Laplace. Oh, getting my methods mixed up here. That's changing from Jacobi to Gauss-Seidel. All I did was change the U. If I just undo that again, I changed the U for the south and for the west nodes to the UK+1. Okay. I run that. Okay, there you can see it only took 18 iterations. So that one change almost halved the amount of work we had to do. Okay, so when in lab sheet 3 I say, okay, use the Laplace.m to help you, that's one of the changes you make, and it's 30 seconds if that. Okay, so what I should have done is save that as something different. Just always make sure you save different versions of your code. I'm going to save that as Laplace.gs, the Gauss-Seidel. Okay, so that's the Gauss-Seidel method. So if you're wondering where that table came from, oops, if I go back to the slides, okay, that came from that code. Okay, so very, very simple. Once you've done one code, once you've written the Jacobi code, the Gauss-Seidel code is dead easy to write because you've done all the hard work. You just have to change the scheme. Okay, so there's the iterations there, 18 iterations compared to 33 for the Jacobi method. Fast is better. You don't want to be hanging around waiting for your code to run. We're only doing it for 6 nodes here. Imagine you're doing it for tens of thousands of nodes. Okay, it's not unusual for code to take days or weeks to run. Okay, so it's for a small example, it's fractions of a second, but for large examples, it can take hours, days, and even weeks to run. So as much time as you can save yourself, better. Okay, that's the Gauss-Seidel method. It's an improvement on Jacobi. It's sort of not quite twice as fast, but it's much faster. We can stop there, or can we? Okay, so there is, what I'm going to do now is teach you another couple of methods which you may not have heard of before. And these are called successive over relaxation methods. Okay, so this is on page 37 in the notes. Okay, well, what a successive over relaxation method does is it slightly alters your indirect method. So normally applied to Gauss-Seidel method, but it could also be applied to Jacobi. But what's the point in using Jacobi when it's slow? So we tend to use Gauss-Seidel. But sometimes there can be 2 types of convergence behavior. One type of convergence behavior is when the iterations bounce about the solution. They oscillate about it. So let's say the solution was 1, and the iterations went 0.5, 1.5, 0.6, 0.4, 1.4. In other words, they go up, above and then below, above and then below, above and below. So they sort of bounce around the solution and converge to the actual solution. Okay, so that's one thing what could happen. The other type of convergence behavior is monotonic convergence behavior, where each successive iteration or each successive estimate converges closer to the actual solution. So those are the 2 behaviors we can encounter. Successive over relaxation method improves on those behaviors. Okay, and what it is it uses a weighted sum of your current estimate plus any updated estimate you have. So let's say you're using Gauss-Seidel to update. Using the successive over relaxation method, what you do is you have a weighted sum of something times your current estimate plus something else times your Gauss-Seidel estimate. Okay, so I'll show you the derivation here. So what I'm going to do is I've said let Rijk be the difference between 2 successive estimates. Okay, so that's just the difference. So you've got one estimate, you use your Gauss-Seidel, you get another estimate, let R be the difference between the 2. Well, if that's the case, a simple rearrangement gives you this. Okay, so the k+1 is equal to the kth estimate plus your difference. And this is where we bring in omega. So that thing that looks like a W is omega, lowercase omega. This is what we call a relaxation parameter. Okay, and we apply it to the difference R. Okay, so our new estimate, the K plus 1 estimate, is the current estimate plus omega times R. Okay, that relaxation parameter, it's what we choose it to be. Okay, every problem will have a different relaxation parameter. Okay, so it's just something, it's kind of what's referred to as a tuning parameter. Okay, it's just what you choose it to be, and you choose it so it gives you fastest convergence. Okay, so this omega is a parameter in the range 0 to 2. Okay, it can't be anything outside that. It's just any real number between 0 to 2. And the value which you set omega can set to alter the convergence behavior. So remember, I noticed there's two types. There's oscillatory convergence, where it keeps bouncing about the solution, and there's monatomic convergence, where it actually goes straight to the solution. Okay, and so when omega is less than 1, the difference between successive iterations is reduced. Okay, because we're multiplying multiplying R by a number which is less than 1. So we're reducing that value of R. Okay, so the difference, we're artificially reducing the difference between two successive iterations. This is used when the method oscillates. Okay, so if you have an oscillatory method, that means you're going too far over the other side. So if we reduce how far we're going, we should get closer to the solution. When omega is between 1 and 2, the difference between successive iteration is increased. Okay, so if we calculate an estimate, a K plus 1 estimate, what we're doing is we're saying, okay, let's move that a bit forward. Let's move that a bit further away than our current K estimate. So the difference between successive iterations is increased. This is what's known as over-relaxation. So when it's decreased, it's known as under-relaxation. When it's increased, it's known as over-relaxation. The actual method is called successive over-relaxation. That's kind of a misnomer, really, because sometimes you under-relax the solution, but it's just known as successive over-relaxation. Right, so when you have an omega between 1 and 2, this is used when the method converges monotomically towards a solution. Okay. When you have omega equals 1, you just got your Gauss-Seidel, or if you've used it, Jacobi method. Okay, so when omega is 1, it's identical to the Gauss-Seidel method. When it's greater than 1, you use an over-relaxation. When it's less than 1, use under-relaxation. There is an optimum value of omega. That will depend upon the problem. Okay, each problem's different, and there are certain methods to finding maximum. The optimum value. Sometimes it's trial and error. Just try out a few different values, and one of them will converge faster. Okay. Okay, so let's have a look at changing our Gauss-Seidel method to take into account this relaxation parameter. So I've just put the Gauss-Seidel method up here. I've done a little trick from this step to this step. Okay. What I've done is I've wanted to include the current estimate. Okay. But I can't just add that without changing this equation. So I've included the Kth estimate for the IJ node there. What I've done here is I've taken it away there as well. So I haven't added anything to the right-hand side. I've added 1 IJ there, and I've added -4 Uij there, but because we're dividing by 4, I'm taking it away. So it's a little trick. So I've added the Uij there, but I've taken it away there. Okay. So if I go back a slide, okay, this was our SOR method. Okay, it was the Uijk plus omega times R. So this means our difference between the Kth plus 1 and the Kth estimate is this fraction on the right. Okay, so that means that must be R. Okay, And what we do is we write it in the SOR form, okay, like this. So we multiply RR by omega, and that's our SOR method. Okay, but since we're multiplying omega by R, we want a weighted sum. So we have a 1 minus omega applied to our current estimate. Okay. So when omega is 1, this first term is 0, just disappears, and we have 1 times the Gauss-Seidel method. Okay. If omega was 2, okay, this would be minus 1 times the current estimate plus 2 times the Gauss-Seidel estimate. Okay. So you can see changing the value of omega changes how much of the Gauss-Seidel method we're applying. Okay, this is what's known as the point SOR method. There are 2 types of SOR methods. This first one is known as point, because we're calculating the values of each point in turn. Okay, so that's just the equation on the previous slide. Okay, the term in the brackets is just the Gauss-Seidel method. So more often we write the SOR method in this form. Okay, 1 minus omega times the current estimate plus omega times, now this U, notice there's a bar over the top. That bar means the updated values obtained using the Jacobi or Gauss-Seidel method. Why would you use Jacobi? You wouldn't, because it's rubbish, so you usually use Gauss-Seidel. But it could be used. You could use a Jacobi if you wanted to. Okay, so this method is known as the point SOR method, or successive over relaxation. Okay, so right, what I'm going to do is I'm going to remember that value of omega, okay, 1.0975, and I'm going to change our Gauss-Seidel code to calculate. Okay, so what I'm going to do is I'm going to save this, and I'm going to just alter the Gauss-Seidel code to use the SOR method. Okay, so I'll save that as Laplace SOR. What was my value of omega again? 1.0975, is it? Go back, check, yeah. Okay, so that's my relaxation parameter. Okay, so if you recall, this was the Gauss-Seidel method, but I'm going to change that to SOR. Okay, so this UK plus 1, okay, that is my Gauss-Seidel method. I'm not going to change that. What I am going to do is I'm going to say, okay, let's apply that successive over relaxation method. So it's 1 minus omega times the current estimate, which is UJI, plus omega times the updated estimate, which we updated on the previous line. Okay, so this step is the Gauss-Seidel step. Okay, we calculated that. Let's over relax it. Okay, and that's using the successive over relaxation. Okay. This is where I do fingers crossed. There you go. So just using successive over relaxation, with Gauss-Seidel it took 18 iterations. SOR it took 13. Okay. Notice I used that value of omega, which is 1.00975. The optimum value will change depending on which what problem you've got. Okay, I didn't just invent that out of my head. There are methods which you can use to actually try and get the best. Okay. So that's SOR. So if you notice, using Gauss-Seidel and SOR, I've hardly made any changes to my Jacobi code. Okay. Right, so that's the SOR solution. If we go back to the slides, there you are. Okay, 13 iterations. So it converges to the solution faster than the other 2. Okay, we can improve on this further still. Okay, SOR is fine, point SOR is fine, but we can improve on it. Okay, this is where line SOR comes in. Now, the point SOR is so called because you're just dealing with each point in turn. Well, what we can do with the line SOR is solve for whole rows or columns of points at once. Okay, and And what we do is we end up writing, if we use a second order finite difference method, we have what's called a tridiagonal array. Tridiagonal array is where you've got a square matrix with numbers or non-zero elements on the main diagonal, the lower diagonal, which is a diagonal just underneath the main diagonal, and the upper diagonal. Okay. Good thing about tridiagonal arrays or tridiagonal linear systems, they're very easy to solve and they're very efficient to be solved. There's a method we can use called the Thomas algorithm, which is very efficient for solving tridiagonal linear systems. Okay. So with the point SOR method can be rewritten so that the current row are the unknowns to be solved. So what we're trying to update, okay, will be on the left-hand side of our system. What we know the values of, i.e. previous values we calculated in the current estimate, or boundary values, form the right-hand side vector. Okay. If you've got more nodes in the x direction than the y direction, then you solve for rows. Okay, so your line SOR, you take a line of rows of points and you solve for that. If you've got more nodes in the y direction than in the x direction, you solve for columns. Okay, so in other words, you pick the row or column which has got the most nodes. Okay, and tridiagonal systems very easy to solve, very efficient to solve. Okay, so this is the principle behind the line SOR method. Okay, I've got some diagrams which are not in your notes. Reason being is I can show this sort of more clearly what's happening here. Okay, so this is a typical 2D array, a 2D finite difference grid. The red nodes are my nodes which I'm calculating the solution to for a whole line at a time. The white nodes are boundaries, the black nodes are computational nodes. Okay, so what you do is if we have more nodes in the x direction than y, we go in a row. So I'm going to solve for all of these red nodes in one go. Then I'm going to move up, and then I'm going to solve for those nodes in one go, and finally move up to the third row, and I'm going to solve for those in one go. So you're solving a whole row of nodes at once. So if I just go back to this one, okay, here we have 5 nodes which we're solving for. What we'll end up, or what we want to end up with, is 5 equations in 5 unknowns. The unknowns will be the value of the nodes. The 5 equations will be formed from the SOR method. Okay. And then once we form a linear system with those 5 equations and 5 unknowns, solve the linear system, you've got your updated values. It might sound like a bit of extra hassle, but it's a lot quicker when we start looking at the computational aspect. Okay. Right. What about what values are unknown and what values are known? Okay, I don't want to get all Dick Cheney on you, but if we go up through rows from bottom to top, let's say we're looking at this row. Okay, all the nodes on this row have already been calculated for the current iteration. Okay, so therefore I know the k+1 value of the south node. The nodes on the current line are what we're solving for. They are unknowns. So we're going to update the value, the k+1 values along this row. The row to the north, we haven't got there yet. So this is still the previous value k. Okay, so we know the values below. We're trying to solve for the values on this row. We don't know yet what the values of the north or the row above is. Okay, so with that in mind, okay, if we move up row by row, Uij would have already been updated to k+1. Okay, so the node to the south would have already been updated. The nodes to the east and west will be our unknown variables, which we need to solve. The node to the north hasn't been updated yet. So what I've done here is I've rewritten our point SOR method, and this is for the, remember this is just for the Laplace equation. It might be different than this depending on what equation you're solving. Okay, if you notice, we got a standard 1 minus omega multiplied by the current node. Okay, all of these now have subscripts k+1 apart from the node to the north. Okay, Well, what I could do there is rearranging so that the current row, the nodes on the current row are on the left-hand side. So the current row means the node to the west, the node ij, and the node to the east. Okay, so I've rearranged those. So they're on the left-hand side. All of these nodes are either already known, okay, so I know the values of all these because this is the node to the south. That's just been calculated on the previous row. This is our current value of node ij. And this is the previous value, okay, from the node to the north. This is a tridiagonal linear system. Okay. It may not be obvious, but that's tridiagonal. So what I'm going to do is I'm going to write it out as a series of equations. So what I've done here is, okay, we're going to solve for nodes going from 1 to n minus 1. Okay, so you notice here the I, okay, so it's our first equation is going to be the first node 1. Okay, we have node 0, which happens to be a boundary node for the first equation, and then we have the node to the right, which is node 2. Okay, so this is for the first node in the row, this is for the second node in the row, etc., etc. And then there's a penultimate node, and there's the one before that. So if you were to write it out, okay, I'm not going to do it for all of them, but if you were to write it out, you can see on the left-hand side, we just have 3 unknowns. Okay, we have a problem. On the left-hand side, we got node 0, okay, and we've also got node n. Okay, so those are the boundary nodes. Now, using Dirichlet boundary conditions, okay, so the ones in red can be moved over to the right-hand side. Okay, if we use Dirichlet boundary conditions, then this node on the boundary is always going to be the same. Right? It's never going to change. So it's going to be the same as the original value for it. And likewise, the node on the other side. Okay, so we know what they are. They're not unknown, so we put them on the other side of the equation. Okay, and you can see they're labeled in red over there. So where you have boundary conditions, when you know them, just whack them over the other side of the equation. That looks quite complicated. This system, when you write it that way, it looks complicated. It's much better to write it out as a matrix equation. Okay, and if we do, we get that. Okay, so that's just this system down here, okay, written as a matrix equation. So we've got a coefficient matrix here. We've got this is our nodes in the current row, and we've got our known values on the right-hand side. Okay, notice the coefficient matrix is tridiagonal. We've got 4 on the main diagonals and minus omega on the upper and lower diagonals. That's not always going to be the case. It'll depend on what equation, what PDE you're solving. Okay, so that won't always be the case, but in this particular example, it is. Okay, so that's our tridiagonal system. Okay. I mentioned earlier, tridiagonal systems are very quick to solve. The way we do that is using quite a popular little algorithm, and this is called the Thomas algorithm. Now, I'm not going to show you where the derivation comes from, but I have included it in the back of the notes if you're interested. Those of you who are doing ODEs, you'll be seeing something called LU factorization next term, and we'll look at a bit there. Okay, but if you are interested where it comes from, look at the appendices in the back. Okay, so we got a trigonal system in the form AX equals some right-hand side vector D. I think I've called it B in the notes, but I called it D on the slides for a reason I'm going to tell you about in a minute. What we do is we let A, B, and C be equal to elements on the lower, main, and upper diagonals of A. Okay, so if I just go back a slide, our A elements, in this case, is going to be minus omega all the way down. Our B elements are going to be all 4s. And our C elements is going to be the minus omega all the way down. Okay, so that's the first thing we do. We say, okay, let A be lower, B be main, C be upper. Then we do a forward sweep. And what we're doing is we're changing our values of C, okay, so but what's actually happening is you're making the values of A be all go to 0 and applying row operations to C. So you're actually doing a form of Gaussian elimination. Okay, so you change your C values and you also change the right-hand side vector values. So D are the right-hand side vector. Okay, if you do that for all 1 to n values in your ABC arrays, okay, you can apply back substitution in this method and that calculates the answer. It is the most efficient algorithm for solving tridiagonal systems. Nobody ever tries to improve on it because you can't. Okay. It's a lovely little algorithm. So if you ever have a tridiagonal system, throw it into the Thomas algorithm, it will give you the solution quite quickly. And this is why we use line SOR, because we know we can solve tridiagonal systems quickly using Thomas algorithm. That's why we're trying to do it via line SOR. Okay, so I mentioned earlier the value of the relaxation parameter changes depending on the problem. Okay, it could be anywhere between 0 and 2. Okay, how do we know what's a good value? Well, the simplest method is to try a few values and see which one gives you the fastest convergence. That's perfectly valid. That's a method I use quite often. Okay, in some cases there is possibility to get the optimum value. Okay, and in particular cases, a tridiagonal system gives us this optimum value. Okay, so here we have a function 2 divided 1 plus the square root of 1 minus rho tj. Now tj is what we call an iteration matrix, and tj is the iteration matrix for the Jacobi method. Okay, I'm giving it to you here as this. Okay, so tj is equal to the inverse of a matrix D multiplied by L plus U. What the hell are L, D, and U? Well, essentially what you want is for D minus L minus U to be equal to your matrix A. So D are the diagonal elements of A, L and U are lower and upper triangular elements of A, but with their signs reversed. Okay. If you would like more information about this, I cover this in my ODE notes. So if you don't do ODEs and want a bit more information, just let me know. But it's kind of something you're going to have to trust me on. Okay, so we can calculate this TJ matrix from A. So that's all you need. So to get TJ, you just need A. This rho TJ, that's the Greek character rho down there. This is what's called the spectral radius. Now it's quite a grand name. It's actually meaning something quite simple. It's just the largest absolute eigenvalue of TJ. So you calculate the eigenvalue of TJ. Calculate if you might have complex eigenvalues. Calculate the modulus. Take the largest one. That is the spectral radius. No one ever calculates eigenvalues by hand. I know we got you to do this last year and the year before, but MATLAB software packages can calculate eigenvalues, so don't ever calculate them by hand, just use a computer. Okay, so what you're looking for rho TJ is the largest eigenvalue of TJ. Okay, so this gives us our optimum value of omega. Unfortunately, we have a bit of a problem. A depends upon omega. So if A depends upon omega, so does TJ. Therefore, so does this. We have an implicit relationship. Omega depends upon something which also depends upon omega. So what we do is we iterate. Okay, give a starting value for omega, a guess value. I usually use 1. Calculate your optimum value. Plug that optimum value back into A. Calculate this again. You'll get a different optimum value. Keep doing that until 2 optimum values agree to some accuracy. That normally takes about 5 iterations. It's not long. Okay, so if you need to calculate it using that, you have to do an iterative process. Or you can just pick a load of values, different values from omega, apply them in the SOR method, and choose the one which converges quickest. You could do that as well. Okay, so using line SOR, what I'm going to do is I'm going to edit our MATLAB program just to show you how we can do this. Now, this is a bit more involved with line SOR. We have to define our A, B, and C arrays. So what I'm going to do is just save this as a different file and call it line SOR. Okay. And A, B, and C don't change throughout all the iterations. They're always constant. So instead of calculating them in here within the loop, what I'm going to do is I'm going to calculate them before. Okay, so I'm going to calculate A, B, and C arrays. Okay. Right, so our B array was, we're going to have 1 to n minus 2 lots of them. Okay, why n minus 2? Actually, n minus 1, sorry. Okay, why am I not going up to n or n plus 1? Ah, but B is the main diagonal though. Boundary, yeah. We know the boundaries, so we don't use the boundary. So B1 to n, 1 to n minus 1. I might have made a mistake there, but I won't know until I've done it. Okay, the A values. Now I'm just going to go back to this one here. Okay, B1 is 4, B2 is 4. Okay, A1 would be up here, but it's not defined. Okay, so A goes from 2 to n minus 1. Okay, we don't have a value of A1, essentially. Okay, so A goes from 2 to n minus 1, and that's equal to minus omega. And C is the opposite. We have the first value of C, but we don't have the last value of C. So C goes to 1 to n minus 2. Okay, so you were right with the if you're off the main diagonal, you have less elements. Okay, and that was equal to 4. Right. Our D, our right hand side D vector, that's going to change. Sorry? Oh, good point. Did I put 4? Yes, sorry about that. Well done. Okay, yeah, thanks for that. I would have caused all sorts of trouble. Okay, the right-hand side vector, this is going to change. Okay, so the ith term on the right-hand side is equal to this horrible thing. So we're going to have to calculate that for each element in our line SOR. Okay, so if I go back to the, okay, so what we have here, okay, yeah, I'm going to get rid of all of this. And do I need to output? Yeah, I'm going to get rid of the inner for loop because what all we're doing with oh no, I'm not. I'm going to tie myself up in knots here. I got an idea. The reason why I'm doing this is a bit of a fudge, but I'm going to use one I prepared earlier. Okay. The reason I'm doing that is you can get into a bit of a mess with all of this. So I don't want to sort of take you down the wrong path. So I've got a class 2. Just have a look at that. See, sorry, just bear with me for a sec. Oh no, that's the wrong one. Oh, that one. Go away. Pass. Ah, here we go. I'm just going to check it's got the Thomas. Yeah. Okay, I'm going to use this one. Right, this is one I did earlier. The reason why I've chosen this one is because you can get into a bit of a tricky thing, and obviously I'm up here sort of lecturing, and it's, you know, you don't normally code when 30 people are watching you. So in other words, I've chickened out. Okay, so for the line SOR, that's what I just did. Okay, A, B, and C, exactly the same as I did before. The bit which I was a bit wary about is, I'm just going to scroll down here. Here we go. Okay, line SOR method. This J loop loops for all the rows. this I loop calculates the right-hand side vector. Okay. By the way, I'm not asking you to do the line SOR method in lab sheet 3. So it is slightly tricky. It's something I wouldn't ask you to do for an assignment unless you really wanted to. Okay, so this is calculating the right-hand side vector D. This is applying the boundary conditions. Okay, so that remember those are the known values. And I solve the tridiagonal system using the Thomas algorithm in that step. Now the Thomas algorithm I've written down here. Okay, this is nobody ever sort of writes this from scratch. You always copy it from somewhere. This is essentially off from Wikipedia. It works brilliantly. Okay, so that's the Thomas algorithm down there. And what I've got up here, which I could show you now, is I've got a method which calculates the optimum value of omega. So here I've calculated the D, L, and U matrices. This is the iteration matrix for the Jacobi method. And this is calculated, I've called it new omega, but this is like the updated value. And that error just keeps iterating until error is less than 12. Okay, so I'm going to just try running this one. Oh, please don't tell me it's not right. Worked. Too many input arguments. The reason it hasn't worked is it's saved it with a space in the way. And I save it as Laplace. Yes, I want to fix it. Excuse me. Now save it as Laplace. Yes, I want to replace it. And run. Okay, so I'm going to use the line SOR method. Okay. The omega, but it calculated the best estimate for the over relaxation parameter was 1.0360. And you can see here, it took just 8 iterations. So if from memory, the Jacobi method took 33, Gauss-Seidel took 18, SOR, point SOR took 13, line SOR took 8. Okay, so as we've gone up and up, as we've gone through those methods, we're getting better and better. There's not much better than line SOR unless you start to get into really complicated sort of niggly things, which you can improve on it, but it's more of a programming exercise than a mathematics one. Okay. So this gives us this output. Okay, just 8 iterations. Let's have a look at comparison. Okay, this is what you'll have to do for lab sheet 3 as well. Okay, those are our 4 methods. These are how many iterations they took. I've also got the CPU time there. Now, iterations are very good, but the line SOR method used a totally different approach. Okay, although the line SOR method only took 8 iterations, it uses more computation per iteration. So I can't just compare the iterations and say this one's quicker, because it might take longer per iteration to do. So it's a common to actually calculate how fast your computer calculated the solution. MATLAB provides a couple of commands called tick and tock, which I kind of like. Okay, I'll show you these working on the MATLAB code here. Okay, what you do is tick. Think of it as a stopwatch. Tick starts the stopwatch. So I've put tick before the while loop, and so it's going to go all through the iterations. And at the bottom, after the while loop, let's scroll down here. I've got CPU equals tock. Tock is stopping the stopwatch. The time that elapses between tick and tock is now in CPU. And so all I've done here is an fprintf statement at the end saying, okay, output the CPU time. Okay. That's what, so if I run that, hang on, if I go back to there, if I run this, okay, run it for, let's say for the Jacobi method, it took 0.0115 seconds. Okay, let's do the same thing, but use a Gauss-Seidel method, put 0089. Okay, so it's kind of a nice little thing to calculate. But check this out, let's run the Gauss-Seidel method again. Okay, so remember 0.0089, it's done it faster. Let's try it again. Done it faster still, what's happening? Okay, and again, 0.0067. You won't get the same CPU time again and again. Okay, what's happening is the operating system in this computer is saying, John's using a lot of MATLAB calls, let's throw in more resources. So that's why it's getting faster. Okay, so what you should really do when calculating this CPU time is run it a number of times, say 10, and take the average. Okay, that will give you a better value for the CPU time. CPU time will also, let's say I'm running YouTube in the background. Okay, that's going to take up some memory. Let's say I've got email open. Let's say I'm doing all this other stuff on the computer. That's going to slow it down. Okay, so CPU time, when you can't compare it between different computers. What I have on here will not be the same as what you have if you do it on your computer. Okay. Furthermore, we can't even compare it on the same computer a day later because I might be running different programs in the background the next day. So you've got to be a bit careful when dealing with CPU time. What I would recommend is run them pretty much at the same time. So run them for the Jacobi, run it about 10 times, calculate the average. Then run it for Gauss-Seidel, calculate it 10 times, then calculate the average. That will give you a fairer comparison. Okay, so that's where the CPU time comes from. This normalized score, okay, what if I wanted to compare this to another author who's got a different computer? Okay, what I've done here is I've normalized it. So I said, okay, we take the slowest time, which happens to be Jacobi, and we divide the CPU times by the slowest time. Okay, so 0.061 divided itself is 1. This is 0.086 divided by 0.061, and we get 0.53. So these are all normalized to the Jacobi time. So this means that Gauss-Seidel took 53% of the CPU time that Jacobi did. Okay. Way down to point SOR, that took just 27% of the time. Okay. So this means, let's say it took 1 hour and 40 to run using Jacobi. It would take just 27 minutes to run using line SOR. Okay, so it's a lot quicker. It is quicker. It may not seem like much, but when you're talking hours, days, weeks, it is useful. Okay, so that's where I got those CPU times, tick and tock function. Okay. Right, so that's essentially going through the indirect methods and solving them. Jacobi, Gauss-Seidel, they're a doddle. Okay, they're quite easy. SOR, you start to up the complexity. Line SOR takes a bit of time to get working. That's why I chicken out of sort of doing the code in front of you. Are there many questions about this? I've talked now for an hour, so not your time to talk now. Are there any questions about what we looked at today? Yep. Oh, yeah. So we've got the Gauss-Seidel method here. You're saying when I change the MATLAB code? Yeah. If I go back to if I can find the code again. Just have to open. Okay. Right. So this is the one I changed. UK plus 1. That is what I've used for my updated values. Okay. U are my current values. So the UK plus 1, it's a whole array. It's not the boundary nodes at all. Okay. So this is just an array containing the updated values. So you. For the first time, good question. Right at the beginning, after I've done the defined a U, I set UK plus 1 equals to U. So for the very first one, if I hadn't have done that, let's comment that out. Okay. Doesn't like it. Why doesn't it like it? Because as you say, it hasn't got a value. Okay. So that's what I did that. That's what I did there. Okay. Any other questions? Control R, Control T. This is many years of working with MATLAB. Yeah, sorry. Control R is just. If I want to comment, Control R, D, R, D. Yeah, you can see I've spent too long on this program. Not on this program, but on MATLAB. It's, yeah. Don't get like me. Any other questions? Okay, so what I'm going to do now is I'm going to just stop the. Oh, we're broadcasting, aren't we?